It's powering the screen you're looking at right this second. It runs our homes, our cities, pretty much our entire world. We just flip a switch and, well, we take it for granted. But what is this invisible force we call electricity? Well, today we're going to pull back the curtain and take a journey from a single tiny particle all the way to the plug in your wall.
So, to really get this, we have to ask the big question right up front. What actually is electricity? I promise, it's not magic, it's just physics. And to understand it, we have to start by zooming in. I mean, way in.
So here's our game plan. We'll start with the absolute building blocks of everything, the atom. Then, we'll look at why some things let electricity flow while others just stop it in its tracks. After that, we'll get into the 3 basic rules of the road for electricity, and finally, we'll see how we actually put it all to work in our daily lives.
Okay, part 1, the unseen atomic engine. See, to get how electricity flows, you first have to understand what it's flowing through. And that means we have to start at the fundamental building block of, well, the entire universe.
And that building block is the atom. Seriously, everything. The copper in a wire, the air you're breathing, even you. It's all just different arrangements of atoms. Now, what you're seeing here is a bit of a simplified model, for sure. But it's a fantastic way to picture what's really going on inside. And inside that atom, you've got 3 main particles. Right in the center, in the nucleus, you have positively charged protons and neutral neutrons just hanging out. But orbiting that nucleus, those are the real key players for our story, the tiny, negatively charged electrons. They are literally the heart of electricity. These electrons aren't just buzzing around all over the place. They stick to specific energy levels, or what we call shells. And it's the electrons in that outermost shell, the valence shell, that are the true stars of this show. How they behave is the key to, well, everything that follows.
So, let's move on to part 2 and see how this all connects. We know electrons are the key, but how in the world do we get them to move? Well, this is all about the difference between conductors and insulators.
And here is the absolute crucial difference. Conductors, like the copper in a wire, have these really loosely attached electrons in their outer shell. I mean, they're practically looking for an excuse to jump over to a neighbor. But insulators, like rubber or glass, their outer shells are super stable. They've got a death grip on their electrons and they just refuse to let go.
This is why a simple electrical cord is the perfect example of how these two work together. On the inside, you've got the copper conductor. Think of it as an electron superhighway. And wrapped around the outside, you have the plastic insulator, which acts like a barrier to keep that powerful flow safely contained and, away from you.
Okay, part 3, the rules of the circuit. So now we know that we can make electrons move through a conductor, but we need to understand the forces that actually govern that movement. This all happens in what's called a circuit, which is basically just a closed loop, a path for those electrons to follow.
The first rule is voltage. The easiest way to think about it is as electrical pressure. Just like water pressure in a pipe pushes water along, voltage is the force that pushes electrons through a wire. So more voltage just means a stronger push. It's why a 9-volt battery has way more push than a little 1.5-volt battery.
Next up is current, which we measure in amps. So if voltage is the pressure pushing the electrons, current is the rate of flow itself. It's how we measure how many electrons are actually moving past a single point every second. Going back to our water pipe, this is the actual volume of water moving through, not just the pressure that's behind it.
So, just how many electrons are we talking about here?
Well, to get just a single amp of current, which really isn't that much, you need this many electrons to flow past a point in 1 second. That is over 6 quintillion. It's a completely mind-boggling number, which is exactly why we just call it an amp.
The final rule of the road is resistance. The thing is, no material is a perfect conductor. As those electrons flow, they're constantly bumping into and colliding with the atoms of the material. This creates a kind of electrical friction that slows the whole thing down, and we call that opposition to the flow resistance.
But here's the really brilliant part. This friction can be incredibly useful. All of those little collisions generate heat. And in something like an old incandescent light bulb, the whole point is to use a material with such high resistance that it heats up until it literally glows. So you see, resistance isn't a bug. In a lot of cases, it's the entire feature.
All right, we're on the home stretch. Part 4, putting electricity to work. We get the particles, we get the rules, so let's look at how this all comes together in the devices we use every single day and the two main ways electricity gets delivered to them.
You know, one of the most powerful things about electricity is its deep, deep connection to magnetism. When an electric current flows through a wire, it creates a magnetic field. But what's really amazing is that the reverse is also true. If you move a magnet near a wire, you create an electric current. This one single principle, electromagnetism, is the engine that drives our world, from tiny motors to the huge generators that power our entire grid.
And that power comes in two main flavors. You've got alternating current, or AC. That's what's coming out of your wall sockets. The electrons are flowing back and forth, constantly reversing direction. Then you have direct current, or DC. That's what you get from things like batteries. The electrons flow steadily in just one direction, from negative to positive. That's why your big home appliances use AC from the wall, but your phone and laptop run on DC from a battery.
Okay, so let's tie this all together. The whole story starts with atoms. Electricity, it's just the controlled movement of their electrons. Conductors are the highways for that movement, and insulators are the guardrails. And that flow is governed by three simple rules. Voltage is the push, current is the flow, and resistance is what restricts it. And finally, we get that power in two ways, as alternating AC from our walls, or as direct DC from our batteries.
So there you have it. From the invisible dance happening inside a single atom to the massive grid that powers our entire civilization. The next time you flip a light switch, just take a second and remember what you're really doing. You are commanding a controlled stampede of trillions upon trillions of electrons, all just to light up your room. Kinda makes you think, doesn't it?